For the longest time, there was this one golden rule in financial modeling. Keep it simple. The smartest model was always the smallest, the most elegant one. But that entire idea, that core belief, is being completely flipped on its head by modern AI. So let's dig into why, when we're talking about financial models today, bigger might actually be a whole lot better.
And this was the old law of the land, laid out by the legendary statistician George Box. For generations of analysts and quants, this was rule number one: no questions asked. The idea has a name. It's called parsimony. And it's pretty simple. If you can explain something with a simple model, you should never, ever reach for a complicated one.
So why was everyone so obsessed with simplicity? Well, it all came down to this one big fear: overfitting. The best way to think about it is to imagine a student who's cramming for a test, but instead of learning the actual concepts, they just memorize the exact answers to the practice questions. Now, they'll ace that practice test, right? But the minute they see a new question on the real exam, they're gonna bomb. A complex model can do the exact same thing. It memorizes the past, every random little blip, but it fails miserably when it faces the future.
And this is where we see a huge clash. The old school models, they played by the rules. They were parsimonious, using just a handful of variables, or what we call parameters. Think of parameters like the tuning knobs on a machine. The old models had maybe 3 or 4. But modern AI models, they come along and just throw the rulebook out the window. They are heavily parameterized. We're talking millions, billions, even trillions of these knobs. From that traditional point of view, this just looks completely insane.
I mean, just to put this into perspective for you, even the early, pretty clunky neural networks they were building for finance had something like 30,000 parameters. 30,000! By the old standards, this was already seen as wildly irresponsible.
But honestly, that 30,000? That was nothing. A drop in the ocean. Today's large language models can have over 1 trillion parameters. The leap in scale is it's hard to even wrap your head around. It's a complete and total rejection of that old principle of simplicity. And here's the real kicker, the part that's so hard to ignore. These ridiculously complex models work. And we know they work on new data they've never seen before. Every single time you use voice recognition on your phone or ask an LLM a question, you're testing it. And their incredible success in the real world is a direct challenge to that decades-old fear of overfitting.
Okay, so all of this creates a massive problem for anyone trying to build a model for something as messy and chaotic as the financial markets. It forces a really, really tough choice.
And this is the choice right here. It's the classic trade-off. On one side, you've got your simple model. It's stable, it's reliable, but it's also kind of dumb. It's a crude approximation of reality. On the other side, you've got the complex model. It's way, way more accurate. It can capture all the little nuances, but it comes with this huge risk of being unstable, of blowing up. So that brings us right to the heart of the matter. If you're an analyst, what do you do? Which path do you take? Is all that extra complexity, all those billions of knobs, actually worth it in the end? Do the benefits of being more accurate outweigh the very real costs and risks?
So, how do we solve this puzzle? Well, it turns out some groundbreaking research gives us a powerful and frankly pretty surprising answer. We've got a whole new theoretical framework for understanding why these massive models work so well, even in the super tough world of finance.
So let's just ask the question straight up. Does adding more and more parameters, cranking up the complexity dial, does it actually lead to better results in financial forecasting? And the main theoretical finding is, well, it's pretty stunning. What this graph shows us is that as you increase a model's complexity, its expected financial return also goes up. But here's the really crucial part. The Sharpe ratio, which is just a fancy way of measuring your return versus your risk, it also keeps going up. So the theory says more complexity isn't just better, it's smarter. You get more reward for the risk you're taking. And what that all boils down to is this one powerful idea: complexity is a virtue. The benefits you get from getting a much better, more accurate picture of the messy reality of markets, well, they completely overwhelm the costs of having so many parameters. It's a total flip, a 180-degree turn from the old way of thinking.
Okay, so a beautiful theory is one thing. It looks great on paper, but does it actually hold up in the real world? Let's check out the evidence and see if this is just an academic theory or something that actually works in practice.
And yep, the proof is in the pudding. When they tested this with real-world financial data that the models had never seen before, the results matched the theory almost perfectly. This graph shows that out-of-sample Sharpe ratio, and just like the theory predicted, performance climbs right alongside complexity. The big, complicated models delivered much better results. Period.
So what's the big takeaway from all this? Well, we're living through a massive paradigm shift. That old rule book that said simpler is better is being thrown out. In the incredibly complex world of finance, it turns out that complexity itself is a feature, not a bug. And the benefits of using these huge machine learning models are, as the researchers put it, totally unambiguous.
And that leaves us with a really fascinating thought to end on. For decades, we all thought the key to understanding complex systems like the market was to make them simpler. But now we're finding out the opposite might be true. Maybe the only way to fight complexity is with, well, more complexity. And if embracing that idea is unlocking new ways to predict finance, it really makes you wonder, what other huge, messy problems, from climate change to discovering new medicines, are out there just waiting for a model that's finally big enough to solve them?